Let the day fall behind you. Find your comfort and let your mind begin to slow. In the quiet, we'll drift softly through what science knows about the dreaming mind. If this quiets your mind, subscribe, and there's always another waiting tomorrow night. In the deep interior of the sleeping brain, where no light reaches and no sound arrives, a wave moves. It is not a wave of water, it is a wave of electricity, brief, coordinated, precise, traveling through the curved tissue of the hippocampus in the first long hours after a person closes their eyes and stills. The cells that generate it fire together in a burst lasting less than 1/10 of a second, then go quiet. Another follows, a few seconds later, then another, each one a sharp wave ripple, named for the shape it draws across the trace of an electroencephalograph, a small steep crest, then falling back to the baseline, clean as a struck string, returning to rest. To the instruments recording it, these ripples look almost too orderly for something happening in darkness, without instruction, without any apparent cause. They look like something being rehearsed, and in a sense they are. These brief coordinated bursts are among the most important events in all of human memory. During waking hours, experiences accumulate. Faces, conversations, the particular quality of late afternoon light on a familiar street, and their raw material is held only tentatively in the hippocampus, that curved seahorse-shaped structure buried deep within the medial temporal lobe. The holding is fragile. Without something to consolidate those traces, to press them deeper into more permanent neural storage, they dissolve like morning breath on a cold window. What the sharp wave ripples do in the quiet of sleep is replay. The hippocampus runs waking experience back through itself, compressing and reactivating the patterns laid down during the day, embedding them into the slower and more stable memory systems of the cortex that surrounds it. And this same mechanism, so essential to the consolidation of waking memory, reaches also into the strange, vivid experiences that occur during sleep itself. Dreams, too, must be replayed. Without the ripple, they are gone before the eyes open. The damage done when this system fails is not abstract. In patients who have suffered significant hippocampal injury, through stroke, through encephalitis, through surgical intervention that once seemed necessary and now looks too blunt for what was lost, the consequence is often a near total loss of dream memory. Not that they stop dreaming. The dreaming continues, but the capacity to carry it across the threshold of waking, to render it into something retrievable and tellable, is gone. They surface each morning from sleep that is neurologically intact and experientially blank. What was vivid enough to feel real a moment before waking is simply not there. The ripple that should have pressed it into place never came, or came too softly, or found tissue no longer able to respond, and so the night is empty. Not silent, the brain was doing something in the dark, but empty of any trace that can be held. This is the first and most essential condition of dream memory. Not attention, not intention, not the habit of keeping a notebook beside the bed. Before any of those, before the dreamer can choose to remember or choose to forget, there must be tissue that can consolidate the fragile neural trace of a dream into something the waking mind can find. The hippocampus and its sharp wave ripples are the beginning of that story. Everything else follows from what they make possible. What they make possible is not uniform, and it does not feel uniform to those who experience it from the inside. Some people move through life as natural dream recallers, waking most mornings with clear, detailed images of where their sleeping mind had gone, sometimes carrying the emotional texture of a dream, through an entire waking day. Others surface into each morning as though from a night that contained nothing at all, certain that they do not dream, often mildly troubled by this certainty in a way they cannot fully explain. The gap between these two populations is not a matter of imagination or effort or any simple difference in the will to pay attention. It is written, at least in part, into the biology of their sleeping brains, into the activity of neural circuits they did not choose and cannot directly govern. And the place that gap first becomes visible, in the research that has tried to map it, is not in the hippocampus alone, but across a remarkable collection of interconnected regions that together form one of the most intricate systems in all of human neuroscience. Roughly an hour and a half after sleep begins, sometimes a little less, sometimes a little more, depending on the person, the night, the accumulation of the day's fatigue, the sleeping brain does something that has no equivalent anywhere in waking life. The eyes, though closed and sealed against the world, begin to move, not randomly, not twitching with the ordinary small movements of muscle at rest. They move in quick, coordinated bursts, left, right, up, diagonal, as though tracking something that is actually there, something the body is oriented toward, even as the body lies almost entirely still. This is the beginning of rapid eye movement sleep, the stage called REM, and what the brain is doing at this moment is as close to a kind of productive interior labor as any state of consciousness offers. The stage was identified in the early 1950s in a University of Chicago laboratory by a graduate student named Eugene Oserinsky and his advisor Nathaniel Kleitman, who noticed that the eye movements in sleeping subjects corresponded with reports of vivid dreaming when the subjects were awakened. That discovery opened a line of research that has not closed. What subsequent decades of study have confirmed is that REM sleep is not passive. It is not the brain powering down. It is the brain doing something specific and essential, something that two researchers in particular, Matthew Walker and Robert Stickgold, have spent careers illuminating. What REM sleep does among its many functions is process emotionally significant memory. It replays, reorganizes, and integrates the emotional charge of experience, separating the feeling from the raw factual trace in ways that allow the waking mind to access what happened without being re-immersed in its full emotional force. This is why sleep deprivation, and specifically selective deprivation of REM sleep, leaves people measurably worse at the emotional regulation that waking life requires. The processing that should have happened in the night did not. The integration is incomplete. And measurably, verifiably, the deficit shows. But for the purposes of understanding why some people remember their dreams and others do not, the most important aspect of REM sleep is not the emotional processing it performs. It is the kind of memory encoding it supports. The neurochemical environment of REM sleep is unlike any other. The brain is flooded with acetylcholine, a neurotransmitter released in high concentrations from neurons in the basal forebrain, saturating the cortex and hippocampus in a chemical tide that does something very specific to the kind of thinking the brain can do. Acetylcholine promotes associative processing, the kind of thinking that moves freely between loosely related concepts, that finds unexpected connections, that generates the nonlinear, emotionally charged, sometimes hallucinatory narrative quality of dreams. It does not promote the sequential, logical, cause and effect encoding that waking analytical thought depends on. The dreaming brain, swimming in acetylcholine, is encoding richly, layering sensation, emotion, association, and narrative in complex overlapping patterns, but it is encoding in a format that does not lend itself to simple linear retrieval. When the dreamer wakes, the brain shifts back toward a different neurochemical balance. Acetylcholine levels fall, norepinephrine and serotonin, suppressed during REM, begin to rise again, and the memory that was encoded in the associative, acetylcholine-rich environment of the dream must now be retrieved by a brain operating in a very different register. It is a little like having written something in one language and needing to read it back in another. The content is there, the trace exists, but the translation across neurochemical states is imperfect, and for most people, on most nights, it fails. The dream dissolves not because it was never real, but because the bridge between the state in which it was made and the state in which memory is accessed is narrow, and most of what was vivid on one side does not make it across. What acetylcholine makes possible, in this sense, is both the richness of dreaming and the difficulty of remembering it. Its presence during REM creates the conditions for experience that is more emotionally textured, more associatively complex, more vivid and strange than ordinary waking thought, experience that is, in principle, more memorable than ordinary experience. And yet the same neurochemical signature that produces that richness makes the encoding resistant to the kind of sequential retrieval that waking memory depends on. This is one of the central paradoxes of dream memory, and it is worth holding for a moment in its plainness. The brain's sleeping mind may be generating some of the most experientially intense episodes of the entire day, and it may be generating them in a format almost perfectly designed to resist being remembered. But some people remember anyway. Some brains on most nights manage the translation. They wake with the dream intact, or nearly so, carrying it forward into the waking morning in sufficient detail to narrate, to feel again, to sketch on a page if the words are not enough. And what the neuroimaging research of the past 2 decades has begun to reveal is that these people, high dream recallers, as the researchers who study them call them, are not simply more disciplined about attending to their dreams upon waking, or more motivated to remember them, though attention and motivation matter too. Their brains are doing something measurably different during the night itself, and the difference shows up in a region that few people have heard of, and that turns out to be one of the most important pieces of the puzzle. The temporoparietal junction sits at the boundary between the temporal lobe and the parietal lobe, near the back and upper side of the brain. It is not large. It is not dramatically visible in the way that, say, the prefrontal cortex announces itself across imaging scans. It is tucked into a fold at the meeting point of 2 regions, a zone of intersection rather than a prominent structure in its own right. But what it does is both specific and consequential. The temporoparietal junction is involved in the integration of information, particularly the integration of signals from inside the body with information arriving from the outside world, and the kind of social cognition that allows one mind to model and understand the perspective of another. It is part of the system that generates the sense of being a self among other selves, the neural machinery of the boundary between inner and outer. Perrine Ruby and her team at the Lyon Neuroscience Research Center have spent years mapping the differences between the sleeping brains of people who remember many dreams and those who remember few. Using functional imaging, they found something that is still being absorbed into the broader picture. The temporoparietal junction shows significantly greater spontaneous activation in high dream recallers than in low recallers, and it shows this difference not only during sleep, but during ordinary resting wakefulness as well. This is not a small or ambiguous finding. It suggests that the brains of high dream recallers are characterized at a resting baseline by more activity in a region that integrates internal and external information and processes the boundary between self and world. During sleep, this heightened activity appears to support the kind of ongoing self-referential monitoring that makes dreams more likely to be noticed as experiences, as events happening to a self, and therefore more likely to be encoded in a form that the waking mind can access. The temporoparietal junction, in this light, is not a memory structure in the narrow sense. It does not store dreams, but it participates in making dreams feel like something that is happening, giving them the quality of experience rather than mere neural activation, the quality of having been somewhere and done something rather than simply having undergone a biological process. And this phenomenological quality, the sense of being present in a dream, of being a self inside it, appears to be one of the conditions that makes a dream memorable at all. An experience that does not feel like an experience does not leave the kind of trace that can be recovered. The temporoparietal junction's activity during sleep may be part of what gives the dreaming mind its sense of inhabiting a world, and that sense of inhabiting a world may be part of what leaves a memory behind. Consider what the brain scans look like when researchers lay them side by side, one from a high dream recaller, one from a low recaller, both from the same night, both from people sleeping in the same conditions of a research laboratory. The scans are nearly identical, the same deep structures, the same cortical regions, the same gross architecture of a sleeping human brain, doing what sleeping human brains have done for as long as there have been sleeping human brains. But at the temporoparietal junction, there is a difference, a region of greater activation, a warmer glow of spontaneous neural activity in the high recaller's brain, visible against the quieter background of the low recallers, like a lit window in an otherwise identical house. The difference is not enormous, but it is consistent. It replicates across studies, across laboratories, across different methods of measuring brain activity. Something is happening in that region, more in one brain than the other, and what it produces, more accessible dream memory, is one of the most fundamental individual differences in human inner life. Alongside this finding about the temporoparietal junction, Ruby's team and others have also examined the default mode network, a set of regions that, in the early history of neuroimaging research, was considered simply the brain's background activity, the noise of a scanner running while a subject waited between tasks. It turned out to be something quite different. The default mode network is a collection of interconnected regions, the medial prefrontal cortex at the front of the brain, the posterior cingulate cortex further back, the angular gyrus tucked into the parietal lobe, that activate together when the brain is not engaged in any specific external task, when the eyes are open and the mind is directed outward toward the demands of a problem or a conversation or a moving target. The default mode network quiets. When the mind turns inward, to memory, to imagination, to the narration of the self through time, it lights up. During waking life, the default mode network is the substrate of daydreaming, of autobiographical memory, of the kind of self-referential narrative that runs beneath the surface of ordinary consciousness. It is where the mind goes when it wanders, and during REM sleep, it does not go dark. The default mode network remains highly active through REM, sustaining the dreaming narrative, the sense of being someone in a particular place, moving through events that have weight and sequence and emotional color in a way that appears to make dreaming, at least in part, an extension of the same self-referential neural activity that underlies the waking imagination. The dreaming mind, in this picture, is not doing something wholly other than the waking mind. It is doing a version of the same thing the mind does when it tells itself stories, in the dark, without the anchor of the senses to constrain it. High dream recallers, the research suggests, show stronger functional connectivity within the default mode network, meaning its component regions communicate more coherently with one another, more synchronously, with signals moving between the medial prefrontal cortex and the posterior cingulate and the angular gyrus in tighter coordination during both sleep and resting wakefulness. Their default mode networks are more integrated, more cohesive systems, and this cohesion appears to support the generation of richer, more sustained, and more emotionally detailed dreaming narratives. A more connected default mode network during REM sleep may produce dreams that have more of the qualities of actual experience, more narrative shape, more sensory texture, more emotional progression, and it is precisely these qualities that make a dream the kind of event that leaves a trace. There is something quietly striking about this. The same network that generates the waking imagination, that sustains the interior monologue, the memory of who we were and where we have been, the capacity to imagine forward into futures that have not yet arrived, is the network that generates the dreaming self. The dreaming mind is not a stranger to the waking mind. It is the waking mind's own narrative function, running in the dark, freed from the constant corrective pressure of sensory reality, producing worlds from the materials of memory and emotion and association. And the brains that are most richly connected within this network during waking hours are the brains most likely to carry the products of that night work back into the morning. There is one more piece of the neural picture worth holding. Spread across the sleeping brain during REM, saturating the cortex in the chemical tide already described, acetylcholine creates a state that is not simply different from waking neurochemistry. It is its inverse in certain essential ways. In waking life, the brain uses norepinephrine, released from a dense cluster of neurons in the brainstem called the locus coeruleus, to support alert, focused, sequential processing, the kind of attention that narrows onto a single thread and follows it through to its conclusion. This is the neurochemistry of directed thought, of linear reasoning, of the kind of memory that can be straightforwardly retrieved because it was straightforwardly encoded. During REM sleep, norepinephrine falls close to silence. The locus coeruleus, so essential to the waking brain's directed attention, reduces its output to almost nothing. And in the absence of norepinephrine, with acetylcholine high and the default mode network running, the brain's associative range expands dramatically. Ideas that would not connect in waking thought connect freely. Emotional associations flow between memories that share a feeling rather than a logic. The narrative of the dream is assembled not by cause and effect, but by something more like mood and resonance, the way one image calls up another, not because they belong to the same story, but because they belong to the same feeling. This associative, norepinephrine suppressed state is both what makes dreams possible and what makes them hard to recover. The suppression of norepinephrine during REM is one of the more absolute neurochemical events in the 24-hour cycle. It is not a reduction in normal waking levels. It is a near cessation, a state of noradrenergic silence that has no parallel during waking consciousness, even in the calmest or most relaxed moments of an ordinary day. And into that silence, acetylcholine pours. The brain that results, temporarily freed from the narrowing, sequential logic of noradrenergic thought, is the brain that dreams. Wide-ranging, emotionally charged, narratively nonlinear, generating images that do not follow the rules of physical causality, and yet feel, while they are happening, entirely real. What all of these mechanisms share, the sharp wave ripples of the hippocampus, the elevated cholinergic tide of REM sleep, the spontaneous activity of the temporoparietal junction, The sustained coherence of the default mode network is that they are happening without any instruction from the waking mind. The sleeper does not send the hippocampus its sharp wave ripples. The dreamer does not choose to elevate acetylcholine or to quiet the locus coeruleus. These processes run according to their own internal logic, following the circadian and homeostatic rhythms that have shaped sleeping brains across the full span of human existence, and longer. The person lying still in the dark is not directing any of it. And yet what emerges from these layered, interlocking, largely invisible processes is experience, vivid, emotionally significant, sometimes more intense than anything that occurred during the waking day. A life happening in the absence of the witness, who usually claims ownership of experience. The question of why some people remember that life and others do not begins here, in the specific configuration of neural activity during sleep, in how actively the hippocampus presses the ripples of dream experience into consolidable form, in how brightly the temporoparietal junction sustains its self-referential monitoring through the night, in how coherently the default mode network connects its nodes into a narrative capable of surviving the transition to waking. These are not matters of will or habit, at least not entirely. They are, at their root, questions of neural architecture, of how a particular brain is organized, how its circuits communicate, how its neurochemistry moves through the night. And they are questions that have, over the last 2 decades of careful research, begun to yield real answers. What the sleeping brain is doing, in other words, is not nothing. It has never been nothing. Long before the instruments existed to record the sharp wave ripples moving through hippocampal tissue, or to measure the cholinergic surge of REM onset, or to map the spontaneous activation of the temporoparietal junction in a dreaming mind, people who woke with vivid and detailed dreams knew, without being able to say why, that something had happened in the night, something that felt upon waking like having been somewhere real, and they were not wrong. The tissue of the sleeping brain, in its curved and layered and still only partially understood complexity, was doing exactly what it appeared to be doing. It was making experience out of memory, and memory out of experience, and running the whole intricate process on neurochemical tides and electrical bursts in the complete absence of daylight or deliberate thought. The default mode network sustains this through the long hours of REM sleep, the medial prefrontal cortex, the posterior cingulate, the angular gyrus, all holding their coherent, synchronized conversation across the dark of the skull, while the body lies as still as it ever lies, and the night outside moves through its own slow phases, and the sharp wave ripples continue their brief, precise passage through the hippocampus, like light moving across water that has been still for a very long time. This is the sleeping brain at work. Not dark, not idle, not simply resting, working in its own register, in its own language, by its own rules, a self-referential intelligence, continuing its labor through the night, building something from the materials of the day, and sometimes, when the conditions are exactly right, leaving enough of it intact that a waking mind can find it in the morning and know that it was there. The dreaming mind does not need the waking mind to witness it. It runs without witnesses, without an audience, without the need for confirmation that what is happening is real. But the traces it leaves in the hippocampus, along the circuits of the default mode network, in the quiet sustained flicker of the temporoparietal junction, are the evidence that something was happening. And in those traces, in the specific and measurable differences between one sleeping brain and another, the question of why some people remember every dream and others remember none begins quietly and at last to take shape. The brain lying in the dark is not dark inside. It is lit in its own register by coordinated electrical activity, moving through tissue that has spent a lifetime learning how to make sense of the world. It is doing, right now, what it has always done, translating experience into memory, memory into narrative, narrative into something that might, if the conditions hold, cross the threshold of waking and remain. The ripples move, the acetylcholine rises. The default mode network holds its slow, connected conversation across the regions of the self, and the night continues, soft and full of something that has not yet been named. A sleeper stirs in the dark. The movement is so small it would leave no impression on a mattress. A slight shift of the head, a brief tensing of the fingers, the eyelids flickering without opening. 3 seconds, perhaps 4, then stillness again, and the breathing deepens, and nothing in the room has changed at all. The clock reads somewhere past 2 in the morning. The dream that was present a moment ago, a room, a voice, some quality of colored light, continues its strange interior weather, and the sleeper sinks back into it as though they had never left. But that small, almost imperceptible surfacing was not nothing. In those few seconds, the dream was closer to the waking world than it had been in the preceding hour. The neural tissue that would need to move the experience from one kind of memory into another had a brief window, narrow as a seam, in which to do it. Whether the dream survives until morning, whether it is still present when the eyes finally open for good, may depend entirely on what happens in moments exactly like this one, scattered through the night, like invisible hinges. Not everyone stirs this way. Some sleepers pass through an entire night without a single detectable awakening, their sleep smooth and continuous, their transitions between stages accomplished without any brush against the surface. In the morning, they report nothing. They did not dream, or so it seems to them. The night is simply dark and blank, and then it is day, and some do not pass through the night this way. Some surface briefly and repeatedly in the narrow gap after a period of rapid eye movement, and sink again. They wake by morning with images still present, with the color and temperature of a place that no longer exists, still faintly available, still reachable if they are careful not to move too quickly. The difference between these two kinds of sleepers is one of the quieter puzzles in the science of the sleeping mind. And the difference, it turns out, is not a matter of how long they sleep or how deeply. It is something subtler. It lives in the architecture of their nights and in certain qualities of the minds inside them. Researchers working with actigraphy, wristband devices that detect even minimal physical motion, and with full polysomnographic monitoring in sleep laboratories, have found that high dream recallers wake more frequently through the night than people who rarely or never remember their dreams. These awakenings are brief. They do not produce the experience of lying awake, watching the ceiling, feeling time pass. They are short enough to leave no conscious trace. But the polysomnographic record catches them, a shift in the EEG signal, a small movement on the actigraphy trace, and then the return to sleep. They tend to occur at the boundary after a REM period, in the minute or two before the brain would otherwise descend into its next cycle. And in those minutes, while the dream is still close, something either transfers or it does not. The logic is simple enough to follow. Dream memory, in its freshest state, is fragile. The neural trace of a dream is not like the memory of a face or an address, something encoded in a stable, rehearsed form. It is more like the impression left by a hand in still water, present for a moment and then smoothed away by the next disturbance. For that impression to become a memory that survives until morning, it needs to pass through a moment of wakefulness, even a very brief one, that allows the encoding process to begin. Without that moment, the experience dissolves, not because it was never there, but because the brain moves on before it can be caught. The researchers who measured this in a sleep laboratory found that high dream recallers had significantly more of these threshold moments across a night, more brief contacts with the surface, and that this difference in waking frequency was present even when total sleep duration was matched between the two groups. It was not about sleeping less, it was about surfacing, briefly and often, in the places where surfacing makes a difference. There is a related quality that shows up in the brain's electrical activity during sleep, and it belongs to the same picture. In studies using electroencephalography, where electrodes placed on the scalp trace the slow and fast electrical fluctuations of the sleeping brain, researchers have measured how the brain responds to sounds played into the sleeping room. A soft tone, a novel or slightly unusual noise, introduced at controlled intervals while the sleeper lies in the dark. The brain, even during sleep, is not entirely closed to the outside world. It continues monitoring at some low and automatic level for things that might require attention. And the question researchers asked was whether high dream recallers and low dream recallers monitored differently. The measurement used is called the P300 response, a particular pattern in the brain's electrical signal that appears roughly 300 milliseconds after a novel or surprising sound, and that reflects the degree to which the brain has registered that something worth attending to has occurred. In waking life, this response appears reliably in everyone who hears an unexpected sound. During sleep, the response weakens or disappears. The brain's sensitivity to outside events turns down like a dimmer, allowing the sleeper to remain undisturbed. But the turn down is not the same in every brain. High dream recallers, when measured during sleep, show a noticeably larger P300 response to the same sounds than low recallers do. Their sleeping brains, though fully in sleep, are registering the outside world more alertly. The boundary between sleep and waking in these individuals appears to be more permeable, more easily crossed in both directions. Sounds reach a little further in. The outside world makes a slightly larger dent. And by the same logic, the inside world, the dream, may reach a little further out toward the boundary where it can be caught before it dissolves. This quality, a more permeable and reactive threshold, may be part of what produces the greater frequency of brief awakenings as well. A brain that monitors more vigilantly will surface more readily in response to internal state changes as well as external ones. The two findings, more frequent awakenings, more reactive EEG response, may be two expressions of the same underlying difference in how the sleeping brain maintains its relationship with the edges of wakefulness. A buried ribbon of tissue running along the inner wall of the lateral sulcus, the deep groove that separates the frontal and temporal lobes, processes what the body is doing from the inside. It registers the rhythm of a heartbeat. It tracks the slow expansion and contraction of breathing. It maps the internal state of the body in something like the way the skin maps its surface, except that what it maps is hidden, running inside, felt as a kind of inner weather rather than as contact with the world. This structure is called the insula, and it is more active and more sensitive in some people than in others. The capacity this tissue enables, interoception, the brain's perception of its own body's internal signals, turns out to be one of the more reliable predictors of how often a person remembers their dreams. Across studies using validated scales designed to measure interoceptive sensitivity, high dream recallers score measurably and consistently higher than low recallers. They are, in ways that can be quantified, more aware of their own interiors. They notice heartbeats and the quality of their breathing and the subtle signals of hunger or tension or warmth with more precision and more regularity than people who move through the day with their attention mostly directed outward. This is not a trivial connection. The dream is, among other things, a product of the body's interior state, a construction assembled partly from the brain's ongoing monitoring of its own biological condition. Cortisol levels, heart rate, the balance of neurochemical tides. These internal signals do not simply run silently beneath consciousness during sleep. They contribute to the emotional tone of dreams, to the urgency or calm of the interior world the dreaming brain creates. A brain that is finely attuned to this kind of signal in waking life may be a brain that generates and encodes dream experiences with greater richness and detail, because the very channel through which the body speaks to the mind is wider and more precisely tuned. The anterior cingulate cortex, which works closely with the insular cortex in processing interoceptive information, is also involved in attention and in the monitoring of internal error signals, the brain's quiet alarm system for noticing when something inside is different from what was expected. These regions together form something like a continuous interior listening system, and in high dream recallers, that system appears to run with particular sensitivity. What this suggests carefully is that the dreaming brain may not be so separate from the waking brain as it seems. The qualities of attention a person brings to their interior life during the day, the fine awareness of what the body is doing, the habit of registering subtle inner states, may shape the degree to which the brain generates internally rich and emotionally detailed experiences during sleep. The organ does not entirely reset. It continues, at night, doing a version of what it was doing all day, with the same instrument, tuned to roughly the same degree. Among the traits that psychologists measure in assessments of personality, one in particular rises consistently from the data on dream recall. It is called openness to experience, and it is one of the 5 broad dimensions that make up the most widely used model of human personality. At one end of this dimension, there are people who prefer what is familiar, who find comfort in the established and the concrete, and who tend not to seek out new sensory or intellectual experiences for their own sake. At the other end are people who are drawn to novelty, to art and ideas, to complexity and nuance, who tend to inhabit their inner worlds with interest and a kind of appreciative attention. Across multiple independent research samples, with many hundreds of participants in total, the score on this single personality dimension correlates positively and consistently with how often a person reports remembering their dreams. The relationship holds across different demographics and different methods of measuring dream recall, from diary studies to retrospective reports. And it predicts not only frequency but character. High openness. Individuals describe their dreams as more vivid, more emotionally complex, and more narratively unusual. Their inner lives when the lights are out appear to match their inner lives when the lights are on, richly detailed, widely ranging, more interested in the strange and the oblique than in the straightforward. Researchers, including Schridt-Herrl and colleagues, who have studied this relationship extensively, have interpreted the correlation as reflecting something about how a person's habitual orientation to inner experience shapes what their dreaming mind produces and how readily it is remembered. A mind inclined toward openness may be a mind that generates more varied and emotionally resonant dream content, and a mind that is also more likely to attend to that content at the moment of waking rather than setting it aside in favor of what the day immediately demands. There is a particular quality of attention that appears in some people more than others, a tendency not simply to experience things, but to be fully inside them, consumed by them, temporarily absent from the ordinary world, and present only in whatever is holding them. A piece of music that causes a listener to lose track of time. A film so thoroughly inhabited that the room around it disappears. A passage of reading in which an hour passes without notice, as though time simply stepped politely aside. This quality goes by a precise name in psychological research. It is called absorption. Absorption is measured by tools designed to capture not what a person does, but how they experience what they do. The most widely used of these is Telegan's absorption scale, which presents descriptions of internal experiences and asks respondents how fully they recognize them, whether they lose themselves in music, whether imagination feels to them like reality for its duration, whether the outside world can entirely cease to exist when something holds their inner attention completely. High scores indicate a trait disposition, a stable habitual way of being present in experience, rather than simply a passing state. And high scores on absorption predict high rates of dream recall, with considerable consistency across the research literature. The person who disappears into music in the evening is more likely in the morning to surface from sleep carrying a dream. The mechanism proposed is not difficult to trace. Dreams, in order to survive the transition from sleep to waking memory, need to be sufficiently salient, vivid enough, emotionally charged enough, internally coherent enough, that they leave a strong enough trace to be retrieved after the biological disruption of waking. A mind with a high capacity for absorption is a mind capable of generating experiences, even purely interior ones, with the full richness and presence of something real. What absorption does in the concert hall or the novel, the dreaming brain may be doing all night long. The inner world, for a high absorption person, is not a pale copy of the outer one. It is a place with its own light and weight. This is the same quality that allows some readers to feel grief at the death of a character they have known for 300 pages, and to carry that grief into their day as though something had actually been lost. It is not a failure of reasoning. It is a precision of imaginative presence, the capacity to be fully where the inner experience is, to commit to it completely, to grant it the full resources of attention, and a dream which arrives with no framing and no distance, in a mind that already knows how to disappear into interior experience, may arrive with a particular intensity that makes it, the next morning, difficult to release. The correlation between absorption and dream recall appears to hold even when other variables are controlled, when openness to experience is accounted for separately, when frequency of waking is separately considered. Absorption carries its own predictive weight, which suggests that the quality of inner immersion is doing something specific in the dream memory system, something beyond what personality dimensions and sleep architecture alone can explain. Consider two people lying in the same dark room, with the same total hours of sleep ahead, the same approximate architecture of cycles and stages, the same quiet house around them. One of them carries a daytime habit of deep imaginative presence, of disappearing fully into music or memory or story. The other moves through their days with attention directed mostly outward, efficiently, practically, without the same pull toward inner immersion. When both of them dream, and both of them will, the dreams may differ in the intensity of their internal world, in the vividness with which the dreaming brain commits to the experience it is constructing. And when both of them wake, the traces may be different in how much they have to offer the reaching hand of memory. This is a portrait, not a prescription. It does not divide people into categories of those who are capable of remembering and those who are not, because the capacity for inner attention is not a fixed thing. It changes with what a person chooses to do with their hours, with the habits they build around stillness, and imagination, with whether they practice the kind of interior listening that absorption at its quietest consists of. The traits involved are real and measurable and partly stable. They are not entirely fixed. A person who scores low on absorption at one point in life may not score the same way a decade later if the intervening years have included regular practice of the kind of inward attention that absorption describes. The trait has biological substrates and developmental roots, but it also has a relationship with what a person does, with the quality of attention they practice, with whether they build the habit of being fully present in their own inner experience. The science does not say the boundary is sealed. The insular cortex continues its quiet work through the night, registering the rhythm of the sleeping body's interior. The EEG electrode on a sleeping scalp picks up the pattern of reactivity, larger or smaller, more or less responsive, that reflects how permeable the sleeping brain's boundary with the outside world happens to be. Neither of these can be seen from the outside. Neither leaves an impression on a room. The person in the dark looks, to any observer, like any other sleeping person, still, slow-breathing, unreachable. What is different lives entirely inside. It is a quality of threshold, a sensitivity of registration, a tilt of attention that has been building across a lifetime of waking experience, and that expresses itself in the dark as the difference between a dream remembered and a dream dissolved. It is worth pausing on what this means for the experience of memory itself. When someone says they do not dream, and many people say this, with confidence, with the calm certainty of long experience, what they are most likely reporting is not the absence of dreaming, but the absence of its traces. The brain research is unambiguous on this point. Dreaming appears to occur across the population in all sleeping brains that pass through REM sleep, which is very nearly every sleeping brain on Earth. The difference between the person who wakes with a vivid interior world and the person who wakes to blankness is not in most cases a difference in whether dreams occurred. It is a difference in whether the conditions were present for those experiences to leave a mark. This reframing is quieter than it might first appear. It does not mean that a vast library of experiences is hidden somewhere, waiting to be unlocked. The traces that do not survive are genuinely gone, dissolved by the neurochemical transition of waking, overwritten by the first incoming sensory information of the day. What remains is not recoverable. But knowing that the experience was there, even without the memory, is a different kind of knowledge. It is the knowledge that the sleeping mind is not idle, not dark, not simply waiting for morning. It is working, creating, processing, and the fact that little of that work survives into the next day does not reduce how much it is doing. The sleeper who stirs at 2 in the morning and sinks back immediately into stillness is not aware of what just happened. The brief window opened and closed too fast for consciousness to register it as anything at all. The dream continued, the body settled, the room held its quiet. But in a brain attuned to its own interior signals, one that registers its own heartbeat with precision, one that monitors the outside world, even in sleep, with a slightly more alert readiness, that brief surfacing may have been enough. The experience of the last several minutes may have crossed the threshold. Some fragmentary trace, a color, a feeling, a shape of narrative, may have begun its passage from the volatile state of sleep experience into something slightly more stable, slightly more durable, slightly more likely to be present still when morning comes. That is the whole mechanism at its most essential, a brain that stirs more easily, a brain that listens more alertly to its own interior, a personality that leans toward openness, toward the richness of inner experience, toward the imaginative immersion that makes even constructed worlds feel fully inhabited. These qualities do not guarantee a dream remembered. Nothing guarantees it. The transition from sleep to waking is always a kind of losing. Some portion of what was present in the night will dissolve regardless. But the qualities that make a dreamer, in the morning after sense of someone who wakes with a world still available to them, are these: permeability, sensitivity, absorption, and the slow cultivated habit of taking the inner world seriously. The boundary between sleeping and waking is real. It is a genuine neurological state transition with measurable markers in every biological system it touches. But it is not the same thickness in every brain. For some people, it is a wall. For others, it is more like a membrane, something that the interior experience can press against and sometimes cross, carrying what it carries, arriving in the morning with evidence of what the night contained. The person who lies in the dark before sleep, fully inside a piece of music, not thinking about it, but living in it, letting it fill whatever space there is between one moment and the next. That person is practicing something. They may not think of it as practice. It may feel like simply what they do, what they have always done, a preference as natural as breathing. But the capacity it represents, the ability to be fully present in an interior experience, to grant it the whole weight of attention, is precisely the capacity that makes the dreaming mind more vivid, more present to itself, and more likely to leave something behind when the night is over. There is a quality of attention that can fill a dark room without any object in it, that can be fully occupied by something that has no physical weight and makes no sound. In people who carry this quality through their days, who know from long experience what it is to be entirely inside something, even something made entirely of imagination, the night has more texture. The hours between sleep and waking have more to offer. And the morning, when it comes, arrives not always empty, but sometimes carrying something back. In the small hours, in a room without light, a sleeper stirs for a few seconds. The threshold opens and closes. Something either crosses or it does not. The dream either leaves a trace or it dissolves. And the difference between those two outcomes lives deep inside the quality of a mind that has been building, through a whole life of waking, the particular kind of inner attention that makes it possible to carry the night forward into the day. That quality of attention, deep, habitual, directed inward with something like patience, is the same thread that connects the person who disappears into music with the person who wakes, some mornings, still knowing where they were. The same capacity that makes the interior world feel real and navigable and worthy of care. The same openness to the inner experience that in the long quiet of sleep keeps something lit enough to survive until morning, like an ember that the dark somehow does not quite extinguish. In the first hour of sleep, the brain descends. It moves through a shallowing of awareness that is also a deepening, through the half-lit threshold of stage 1, where the body still twitches and the mind still clings to the day's last loose images, and then down into stage 2, where the spindles fire and the muscles let go, and the sounds of the room grow faint and irrelevant. The descent continues. Slow waves begin to roll through the cortex, long and unhurried, like swells crossing deep water. The body's temperature falls by 1 or 2 degrees. The heart slows, the breath slows, and the first cycle of the night settles into its deepest architecture, slow wave sleep, where the brain is as quiet as it will ever be, while still alive. Then, roughly an hour and a half in, something shifts. The slow waves thin out, the deep sleep lighten, the body climbs back through stage 2 and pauses briefly before turning in a direction that has no waking equivalent. The eyes begin to move, not slowly, not absently. They move in rapid, purposeful bursts, tracking something that is not there. The breath quickens. The heart beats unevenly. The brain, measured at the scalp by electrical leads, produces a pattern that looks almost indistinguishable from wakefulness. The same fast, low-amplitude waves, the same spread of activation across the cortex, and yet the body lies entirely still. The large muscles of the limbs and trunk are held in a state of active paralysis by signals originating in the brainstem, a temporary softening of the body's ability to act, so that what the mind is doing cannot be translated into motion. The first REM episode of the night has begun. It lasts perhaps 5 minutes, 6 minutes, no more than 10. In those minutes, something is happening in the sleeping brain that is unlike anything that occurs in waking life. Memory traces from the day are being replayed. Emotional content is being processed and reorganized, its edges softened or sharpened, its significance recalibrated against everything the brain already knows. The hippocampus and the amygdala are in active conversation. The prefrontal cortex has relaxed its usual supervisory grip on narrative logic, which is why the images that arise during this sleep can be strange, non-linear, geographically impossible, and yet feel, while they are occurring, entirely real. The first dream of the night is forming. It is brief. It is thin compared to what will come later, but it is real in the only sense that matters inside a sleeping mind. It is being experienced completely by the brain that is generating it. Then it ends, the cycle turns again, and the brain descends once more towards slow-wave sleep. The second cycle begins its long passage through deep sleep, and the body continues to repair itself. The growth hormone rises, the immune system works, the cellular maintenance that waking life cannot spare the energy for runs quietly through the night. This second descent into slow-wave sleep will be somewhat shallower than the first and somewhat shorter. The pattern is not random. It is a structure built into the human organism across millions of years, a reliable rhythm that repeats through every full night of sleep in approximately 90 to 110-minute intervals, the interval itself varying slightly from person to person and night to night, but consistent in its general architecture across essentially all healthy human adults. These cycles are called ultradian rhythms. Ultradian meaning shorter than a day, rhythms that loop faster than the great 24-hour circadian cycle that governs when the body wakes and when it sleeps. The word itself is less important than the shape it describes, a regular oscillation, like a tide that comes in and retreats and comes in again 4 or 5 times across the course of a normal night, each passage leaving something slightly different behind. When the second cycle reaches its REM episode, something measurable has changed. The REM period that arrives at the end of the second cycle is longer than the first. Where the opening REM episode ran for 5 or 6 minutes, this one may run for 12 or 15. The dreaming extends. The narrative has more room to develop. The scenes have more time to change and deepen. And when the second cycle passes and the third begins, the pattern continues. The slow-wave sleep in the second half of the night becomes thinner, less deep, sometimes disappearing almost entirely, and the REM periods grow longer and richer in their place. By the third cycle, a REM episode may last 25 minutes. By the fourth, it may stretch to 35 or 40. In the final cycle of a full night, the REM period can extend to 45 minutes or beyond, nearly a full hour of dreaming, narratively complex, emotionally saturated, and occurring just before the moment of natural waking. The shape this creates, when drawn out as a diagram plotting sleep stages against time across a full night, has a name, a hypnogram. It looks from a distance like a staircase that descends steeply in the early hours and then gradually rises back toward the surface, with the bands of REM sleep spreading wider and wider as the night progresses. The deep, dramatic, slow-wave descents of the first two cycles give way, in the second half of the night, to something flatter and more complex, long plateaus of REM punctuated by brief, shallow passages of lighter sleep, the brain moving back and forth across the threshold of dreaming like a tide that cannot quite decide to leave. That image is more accurate than it might seem. The force driving the brain toward more REM sleep in the later hours of the night is not simply exhaustion or chance. It is a biological push, a measurable pressure arising from two distinct but cooperating systems. The first is the homeostatic drive for sleep itself, the accumulated need for sleep that builds from the moment of waking and slowly dissipates across the night, and whose particular appetite for REM sleep is satisfied less efficiently in the early cycles, leaving a residual pressure for more that grows stronger as the hours pass. The second is the circadian system, the body's internal clock governed largely by the suprachiasmatic nucleus in the hypothalamus, a small cluster of cells that times the biological events of the day and night with extraordinary precision. In the hours before natural waking, these two forces align. The circadian system's drive toward REM sleep crests in the early morning. The homeostatic REM debt, accumulated across the earlier cycles, adds its own pressure. Together, they produce a biological environment intensely favorable to extended, vivid dreaming. The brain is pushed toward REM sleep with more force in these final cycles than it experienced in the first, and the dreams that result reflect that intensity directly. The period between roughly 5 and 8 in the morning, in a person sleeping on a conventional schedule, is the peak of this phenomenon, the late-night REM rebound, some researchers call it, though the word rebound suggests a bouncing back from something which does not quite capture it. It is not a correction, it is a culmination. The long arc of the night's architecture bends toward this point, the sleep system reaching its most fertile dreaming territory in the last hours before the body would naturally open its eyes. This is where the most vivid dreams live. Not the dreams that arrive in the first thin slice of REM at the end of the opening cycle. Those tend to be brief, lightly threaded, closer to imagery than to narrative. The dreams that last, the ones that are still present in the first moments of waking and that carry a sense of having been somewhere fully real, are the late-night dreams, the dreams from the fourth and fifth cycles. The dreams that had 30 or 40 uninterrupted minutes to develop their scenes, to move through emotional arcs, to generate the kind of layered, internally consistent experience that leaves a trace strong enough to survive the crossing from sleep to wakefulness. There is a difference between dreams and sleep thought, and it matters here. Even in the parts of the night where REM sleep is not occurring, the sleeping brain is not entirely quiet. During stage 2 sleep, and even during the slow-wave deep sleep of the early cycles, mental activity continues. Researchers who wake people from NREM sleep and ask them to report what was happening in their minds find that something is often there, a fragment, a sense, a half-formed idea. But these NREM experiences have a distinctive quality. They tend to be less visual than NREM dreams. They are more conceptual, more thought-like, more closely related to waking cognition in their structure. They may feel like a problem being turned over, or a feeling without a scene attached to it, or a voice without a face. They are shorter, less emotionally intense, and far less likely to generate the kind of narrative complexity that tends to survive into waking memory as a reportable dream. Some researchers characterize these nighttime and REM experiences as sleep thought, distinguishing them from the fully realized perceptual world of REM dreaming. The distinction is not absolute. There are NREM reports that sound convincingly dreamlike, and there is scientific debate about exactly where the boundary lies. But the practical difference in terms of what people remember upon waking is real and consistent. The mental content of NREM sleep, even when it leaves some trace, tends not to be the content people describe when they say they remember a dream. The content people carry back from sleep into the morning, the scenes and faces and emotional textures that feel like memories of another place. That content overwhelmingly originates in REM, the deepest slow-wave sleep of the night, which clusters heavily in the first two 90-minute cycles, is the stage least associated with recalled dreaming. This is the sleep most associated with physical restoration, with the release of growth hormone, with the clearing of cellular waste products from neural tissue. The brain during slow-wave sleep is doing essential biological work, but the work it is doing is not primarily the work of narrative construction. The slow waves that roll through the cortex during deep NREM sleep are characterized by widespread synchrony, neurons firing and falling silent together in long coordinated rhythms, and this synchrony, while essential for certain kinds of memory consolidation and for the restorative biology of sleep, is not the neural environment in which vivid, emotionally complex dreaming thrives. REM sleep is the opposite in almost every measurable sense. During REM, the synchrony breaks down. The cortex becomes desynchronized, different regions firing with different timing, different rhythms, the pattern of activation complex and variable, rather than locked into the slow rolling waves of deep sleep. The brain, during REM, is not idling. It is doing something closer to improvising, drawing connections across distant memory systems, activating limbic circuits, running the narrative engine of the dreaming mind on a substrate of cholinergic activation and relative noradrenergic silence. The visual cortex fires without any visual input from the eyes. The motor cortex prepares movements that the body's paralysis will never execute. The emotional processing regions run at high activity, responding to the content of the dream as if it were real, because within the architecture of the sleeping brain, it is. And the intensity of all of this increases across the night. Dream density, a term researchers use to describe the subjective richness of a dream, its frequency of scene changes, the emotional complexity of its content, the number of characters and locations and narrative threads it contains, is not constant across the night's REM episodes. The first REM dream is thin compared to the last. This thickening of dream content over successive cycles reflects in part the shifts in neurochemistry that occur across the night. Acetylcholine, the neuromodulator that dominates REM sleep, builds an activity across the night's later cycles, creating a progressively more plastic and associative neural environment in which the dreaming brain can generate richer and more internally complex experiences. Cortisol, the body's primary stress hormone, also rises across the night in a slow, steady arc, peaking in the hours just before natural waking. Cortisol's role here is not stress in the common sense of that word. Its rising concentration across the pre-dawn hours is a normal feature of the healthy sleep cycle, part of the body's preparation for the metabolic demands of waking life. But its presence also amplifies the emotional coloring of late-night dreams. The amygdala, particularly sensitive to cortisol, becomes more reactive as cortisol rises. The emotional content of dreams in the final cycles of the night is in part a reflection of this neurochemical environment, the brain dreaming in a state of heightened emotional sensitivity, producing experiences that feel more charged, more urgent, more vivid, more real. This is one reason the last dream of the night is the one most likely to be remembered. It is not only because it is the most recent, though proximity to waking matters significantly. It is because it was the most vivid, the most emotionally saturated, the most fully realized. It had the longest uninterrupted REM period to develop in. It was produced by a brain operating at peak cholinergic activity, bathed in pre-dawn cortisol, pushed by both homeostatic pressure and circadian timing toward the richest dreaming state the night can generate. All of these forces converge on that last REM episode, and the dream that forms within it is in a real neurobiological sense, the dream the night was building toward. But there is another factor that determines whether even this dream makes it into waking memory, and that is the quality of the awakening itself. The transition from REM sleep to full wakefulness is a fragile neurobiological crossing. Dream memory is not stable at the moment of waking. It exists, briefly, in a state of heightened accessibility. The neural trace is fresh. The emotional signature is still active. The brain is still close to the state in which the dream was generated. But this accessibility window is short, minutes at most, and the conditions under which the crossing from sleep to wakefulness happens have an enormous influence on whether the dream's trace survives into long-term accessible memory or dissolves in the interference of the waking world. A gradual awakening from REM sleep, of the kind the body produces naturally when it has slept enough, and the light is changing and the night is ending on its own terms, preserves dream memory far better than an abrupt one. In a natural awakening, the brain lingers at the threshold. There is a slow brightening of awareness, a reluctant loosening of the dream's hold, a brief period in which both the sleeping mind and the waking mind are simultaneously present, the dream still visible, the room just beginning to register. This is the window in which dream memory can be caught. The neural trace is intact. Attention can be directed toward it before the incoming sensory information of the waking world, the light, the sounds, the physical demands of the body, begins to override it. An alarm clock does something very different. When an alarm drags the brain from deep NREM sleep, from the slow wave stages where the body is most profoundly disengaged from consciousness, there is no lingering at the threshold. The transition is not gradual. The brain is pulled from the deepest quiet it will experience all night and deposited abruptly into full wakefulness, a neurological rupture that leaves behind no accessible dream content because there was no REM sleep in progress when the alarm fired. But even when an alarm wakes the brain from REM sleep, the abruptness of the transition creates a surge of sensory interference, sound, urgency, the immediate orientation toward the demands of the day that overwrites the fragile, still forming trace of the dream before any consolidation can occur. The dream was there, then the alarm sounded, then it was gone. This is not a failure of memory. It is a collision between two incompatible neural states, happening too fast for the bridge between them to hold. The timing of the alarm relative to the sleep cycle matters in a way that has measurable consequences. Waking from REM sleep produces dream recall. Waking from slow wave sleep does not. The person who sets an alarm for 6 in the morning and wakes from the deep NREM sleep that still dominates their second or third cycle at that hour will wake groggy and dreamless, the technical term for this being sleep inertia, a heaviness of cognition that reflects the brain's resistance to being dragged from deep slow wave. The person who sleeps until 7:30 or 8, moving naturally through the final long REM periods of the night, and waking from the last of them in a gradual brightening, will almost always wake with a dream. The clock of the sleep cycle does not care about the clock on the wall. It moves on its own schedule, driven by biological timers that evolved long before mechanical timekeeping existed, and those timers place the richest, longest, most dream-dense sleep in the hours that morning alarms most reliably cut short. This is one of the less discussed consequences of early rising, not simply a reduction in total sleep time, but a specific and disproportionate reduction in the latest and richest REM sleep, the sleep that generates the most vivid dreams and provides the most accessible dream content upon waking. The person who wakes at 5:30 to an alarm is not simply waking early. They are, in the language of the sleep cycle, cutting the night off at its most generative point. There is something almost architectural about the way a full night's sleep is organized when it is allowed to complete itself without interruption. The early cycles build the foundation. The early cycles build the foundation. The slow-wave deep sleep of the first and second cycles restores the body, consolidates declarative memories, clears the metabolic byproducts of the waking day. This work is not optional. It is the biological price the body pays for continued existence, and the sleep system prioritizes it. The first cycles spend more time in deep sleep, not as a choice, but as a consequence of accumulated need. The homeostatic pressure for slow-wave sleep is highest at the start of the night and is paid down most efficiently in those early cycles. By the time the third and fourth cycles arrive, that debt is largely settled. The slow-wave sleep thins, the architecture shifts, and the system begins to spend the night's remaining time differently, in the longer REM episodes that the first cycles did not have room to accommodate. The structure is in this sense functionally intelligent, not because the sleep system plans anything, but because the mechanisms that regulate sleep stage timing were shaped over long time to serve complementary biological needs in a sequence that works. The early night builds and repairs. The late night processes and dreams. And there is one more quality of the late night REM sleep that bears naming directly, because it connects to the question of why some people remember their dreams so consistently, while others remember almost none. The final REM episodes of the night are not only the longest and the most vivid, they are the most proximate to waking. After the last REM episode of the night ends, the body is close to waking on its own. The circadian drive toward wakefulness is rising. The sleep system is settling toward its threshold. The brain is only a short distance, neurologically, from full consciousness. This proximity means that the transition from the final REM period to wakefulness, whether natural or interrupted, is inherently closer to the gradual brightening that preserves dream memory than the abrupt plunge from deep slow-wave sleep that erases it. A brain waking naturally from the last REM period of the night is waking from a state that was already close to waking. The gap it needs to cross is smaller. The trace of the dream is warmer, more recent, more easily caught by the waking attention that is just beginning to organize itself into a day. This is the window. It is not a metaphor. It is a neurobiological interval that is measurable, approximately 2 minutes long in optimal conditions, during which the dream's neural representation remains accessible enough to be encoded into a form of memory that can survive the full transition to wakefulness. Within those 2 minutes, the fragments of the dream can be caught, not as a complete narrative, not as a faithful record of everything that happened, but as enough, a face, a quality of light, a feeling, a word, a motion. From these fragments, the broader dream can sometimes be reconstructed. Without them, nothing remains. The dream existed completely, and then it did not. The morning is full of these brief vanishings. In any city, on any morning, thousands of people are lying still in the last minutes before they wake, in the final slow brightening of a dream that is already beginning to thin. Some of them, without knowing why, will pause before reaching for the phone or sitting up. They will lie still for a moment in the unfamiliar warmth of a dream they cannot fully name, and something, not quite a decision, more like a reflex of attention, will hold them there long enough for the trace to deepen. Others will move immediately, and the movement will be enough to break the connection. The trace will dissolve in the first sensory impressions of the morning, and nothing will remain to remember. Both experiences happen in the same bedroom, to the same body, in the same biological architecture of sleep. The difference is measured in seconds and in the quality of stillness. What determines which outcome occurs has something to do with habit, and something to do with attention, and something to do with the depth of personality traits that do not change easily or quickly. But underneath all of those factors, the sleep cycle itself is doing its work, building toward those final long REM periods all night, concentrating the most vivid and emotionally complex dreaming into the hours closest to natural waking, and handing the sleeping mind, 4 or 5 times a night, the brief and fragile gift of a dream that might survive. The hypnogram, that visual record of a full night's sleep, does not look like a picture of something particularly important. It looks like a graph, lines moving up and down across horizontal time, labeled stages, stacked in a narrow band between the hours of 11 at night and 7 in the morning. It is modest in its appearance. It does not look like a map of a night's worth of experience, but follow the REM bands from left to right across that diagram, from the thin sliver of the first cycle to the wide extended plateau of the 4th and 5th, and the arc becomes clear. The night is not uniform. It does not deliver the same kind of sleep at midnight and at 6 in the morning. It changes, it develops. The architecture of the night is a progression from restoration toward experience, from the deep biological maintenance of the early hours toward the rich, emotionally alive dreaming of the late ones. The body settles into deep sleep first because it must. It climbs toward long REM last because, having done what was necessary, it can, and in the final cycle, in the longest and richest REM period of the night, in the 40 or 45 minutes of dreaming that occurs in the hour before natural waking, in a person who has slept long enough, the brain is doing something that leaves a trace. Unlike anything produced by waking experience, it is assembling a world from memory. It is running the narrative circuits of the default mode network without the anchor of sensory reality. It is processing emotion in a state of relative noradrenergic calm that gives the dream its particular quality: vivid but not anxious, intense but smooth and internally consistent, in a way waking emotion rarely manages. And then gradually, the room begins to lighten. The sound of the morning comes in faintly, a bird or traffic, or the changing quality of silence that follows a long night. The body's temperature begins to rise toward its morning peak. The brain, still in REM sleep, still generating the final images of its last dream, begins the slow process of reassembly toward wakefulness, the long neural conversation between sleep and waking that happens when the night is allowed to complete itself over the course of minutes, rather than the fraction of a second it takes an alarm to cut it short. In those minutes, the dream is still present. The final image holds a figure in a half-lit space, or a motion across water, or a sound carrying the particular quality of something that happened but did not happen. The brain is beginning to register the room, but has not yet released the dream. Both are present simultaneously. The the constructed world of the dream and the sensory world of the morning, overlapping briefly in the neural field of a waking mind. This overlap, brief and fragile, and occurring only in the unhurried natural waking from the night's last REM period, is where dream memory is made. The night builds toward it, steadily, from the first thin 5-minute REM episode of the opening cycle to the long, rich dreaming of the final one, each cycle a step in an architecture designed by the slow logic of biological development over vast time to place the most vivid and the most accessible dreaming exactly at the moment when the sleeping brain is closest to waking. The most vivid dream of any night is almost certainly happening in the last hour before the eyes open on their own, in the final long REM period of a sleep that has been allowed to finish, in a brain that has worked through the night and arrived at last at the part of sleep where the night's most complete experience waits and quietly holds. In the brainstem, tucked close against the floor of the fourth ventricle, there is a cluster of cells so small it could be covered by a fingernail. It is dense and blue. Its name in Latin means blue place, and during most of the waking day, it fires in a slow, steady rhythm, releasing its chemical signal into the brain above, like a low, continuous hum. But as REM sleep deepens through the night, something happens to that hum. The cells grow quiet. One by one, their firing rate falls. And in the last hours before dawn, when the body has been still for many hours, and the mind is somewhere else entirely, those cells go nearly silent, their output dropping to almost nothing, a stillness unlike anything else in the 24-hour cycle. This small blue cluster is the locus coeruleus, and what it stops releasing when it goes silent, norepinephrine, the brain's signal of alertness and linear attention, may be one of the most important chemicals in the whole story of why some dreams are remembered and others are not. The silence of the locus coeruleus is not an accident of sleep. It is a precise neurobiological event, timed to REM with remarkable consistency, and it creates a chemical environment in the dreaming brain that has no waking equivalent. Without norepinephrine pressing the cortex toward focused sequential processing, the brain shifts into a different mode entirely, associative, fluid, rich with emotional color, and open to connections that would never form in daylight. The dreaming mind becomes, in those silenced hours, something closer to a tide pool than a river, still enough for strange things to surface. What drifts up in that stillness, and how deeply it is encoded into memory, depends partly on how completely and how precisely the locus coeruleus makes that transition from Hume to silence. Individual differences in the timing and completeness of this silencing are subtle, measurable at the level of neurophysiology, and may contribute in ways that are still being worked out to differences in dream vividness and the emotional salience that gives a dream its best chance of being remembered. The body lying in the dark does not know it is running an experiment. It is simply sleeping. But in the hours between falling asleep and waking, the sleeping brain moves through conditions that no waking state replicates, conditions that make certain experiences more memorable than others, certain minds more receptive than others, and certain nights richer than any ordinary night of waking life. These conditions are partly universal, following the same basic architecture in almost every human nervous system, and they are partly individual, shaped by chemistry, by structure, by the long influences of hormones and genes, by the specific biological history of this particular brain, in this particular body, on this particular night. Norepinephrine is not the only neuromodulator that matters here. Deep in the basal forebrain, neurons rich in acetylcholine begin their most active phase during REM sleep, flooding the cortex with a neurochemical signal that promotes associative, emotionally textured encoding, the kind of memory formation that catches images and feelings rather than logical sequences. The suppression of norepinephrine and the surge of acetylcholine happen together, and together they define the neurochemical signature of the dreaming brain, a signature that is, in some measurable ways, more present in some people than in others. The completeness of noradrenergic silence, the depth of cholinergic flooding, these are not uniform across all sleeping brains, and the variation between them is real enough to influence what any given night of dreaming leaves behind. There is a small gene, or rather a small variation within a gene, that researchers have looked at carefully in this context. The gene is called SLC6A4. It produces a protein that transports serotonin back into neurons after it has been released, a recycling system that regulates how much serotonin remains active at the synapse at any given moment. In the promoter region of this gene, there is a common variation. Some people carry what is called the long form, and some carry the short form. The short form is associated with lower efficiency of serotonin recycling and with greater reactivity in the amygdala, the brain's emotional significance detector, when that person encounters something emotionally charged. The amygdala in a person carrying the short form responds more strongly, more quickly, and with measurably greater activation to stimuli that carry emotional weight. And during REM sleep, when the dreaming brain replays and reorganizes emotionally significant experiences, a more reactive amygdala may mean that the experiences passing through it carry more emotional charge, enough charge to imprint more deeply, to survive the fragile transition from sleep to wakefulness, and to arrive in conscious memory with enough weight to be noticed and recalled. This is a hypothesis, carefully constructed and plausible, not a settled finding. The links in the chain, from serotonin transporter variation to amygdala reactivity, to dream emotional intensity, to dream recall, are each supported by real evidence, but the full chain has not been confirmed end to end in a single study. What is known is that amygdala reactivity matters for dream memory, that the serotonin transporter gene shapes amygdala reactivity, and that the short allele is common enough in the general population to represent a genuinely widespread source of individual variation in how emotionally alive the sleeping brain becomes each night. In some brains, the amygdala during REM sleep is a quiet witness to the passing mental imagery. In others, it is an active participant, marking certain moments with urgency, with feeling, with the neurochemical signal that means hold this. This matters. Do not let this go. The amygdala responds to the emotional content of what the dreaming brain generates, but it does not do this work alone. Across the sleeping cortex, a network of regions that are most active when the mind turns toward itself, toward memory, toward personal narrative, toward the mental simulation of experience, sustains its activity through REM sleep with a persistence that distinguishes the dreaming brain from almost any other state. This is the default mode network, a constellation of regions spanning the medial prefrontal cortex, the posterior cingulate cortex, and the angular gyrus, connected by slow synchronized activity that hums through the sleeping mind like a low chord. In people who frequently remember their dreams, this network shows stronger functional connectivity during REM sleep than in people who rarely do, a difference detectable not only during sleep but during quiet waking rest, suggesting that the default mode network's tendency toward rich internal activity is not a state but a trait, written into the resting organization of the brain itself. The medial prefrontal cortex sits at the front of this network, above the eyes and behind the forehead, and it carries a specific role that is relevant here It is involved in self-referential processing, in the sense of being a subject with a perspective, an interior, a history. During REM sleep, its activity is one of the signatures of the dreaming state, and in high dream recallers, its activity is both stronger and more sustained than in low recallers. The distinction is not dramatic on a single scan, but across a population, it is consistent, replicable, and structurally grounded. Research by Perrine Ruby's team found that high dream recallers show greater gray matter volume in both the medial prefrontal cortex and the temporoparietal junction, a region that sits at the meeting point of the temporal and parietal lobes and is involved in the integration of self and world, inside and outside, self-perspective, and the perspective of others. More gray matter in these regions means more neural substrate for the kinds of processing that generate and sustain the dream narrative, and more substrate for the metacognitive activity that notices the dream as something happening, something worth attending to, something that might be carried back. A structural MRI shows the difference in cross-section. Two brains, anatomically very similar, but with a region of subtly greater density, glowing faintly at the medial prefrontal cortex of one of them. The difference is visible without any behavioral test, without any interview or questionnaire. It exists in the tissue itself. And this raises a question about cause and effect that does not resolve cleanly. Did this person grow more gray matter in the medial prefrontal cortex because they spent years attending to their dreams, reinforcing the neural circuits involved in self-referential processing through the sustained act of noticing and remembering? Or were they always more inclined to attend to their dreams because they were born with more neural substance in those regions? The most honest answer is probably both. Neural structure shapes behavior, and behavior, sustained over years, shapes neural structure in return. Attention leaves a physical trace. The habit of turning inward, of catching the faint residue of a night's dreaming and following it back toward the source, may itself be one of the forces that gradually builds the brain that is best at doing it. The temporoparietal junction, that quiet landmark at the meeting of two lobes, deserves a moment of its own. In Ruby's research, this region was one of the most reliably distinguishing features between high and low recallers, more spontaneously active during sleep, more structurally developed, more consistently engaged. It is a region associated with the sense that there is a self here, with a point of view distinct from the world outside. And during dreams, that sense of self, with a point of view, is precisely what animates the narrative. The dreamer who moves through the dream, who notices things, who feels the emotional weight of what is happening, who is present as a character rather than just an observer of disconnected imagery. A more active temporoparietal junction may mean a more inhabited dream, a dream with a stronger central perspective, a more coherent subjective presence, and therefore a richer, more structurally organized memory trace that is more likely to survive the journey back to waking. Consider what a brain scan of two sleeping people might show, laid side by side. In most regions, the two scans look nearly identical. The slow waves of NREM sleep move across both in the same rhythm. The visual cortex dims in both at roughly the same rate. But at the temporoparietal junction, a small warm region of difference glows in one scan and not the other, an area of greater activation in the person who will wake in the morning with a dream to describe. This difference is subtle enough that it would not register without careful measurement, but it is consistent enough that in a large enough sample it predicts with genuine imperfect probabilistic reliability who will remember and who will not. The brain that remembers is not dramatically different. It is shifted, slightly, in a few specific places, in ways that accumulate. Sleep itself changes across a lifetime, and the changes are not gentle. At birth, something close to half of all sleep time is spent in REM, an extraordinary proportion, reflecting the developmental importance of REM for the formation and refinement of neural circuits in a brain that is still being assembled. That proportion falls through early childhood, drops again through adolescence, and continues a slow, steady decline through middle and later life. By the time a person reaches their 60s or 70s, REM sleep occupies a significantly smaller share of the night. The REM episodes themselves are shorter, less consolidated, and less dense with the eye movements and neural activity that mark the deepest stages of dreaming sleep. The late-night REM rebound, that biological push toward extended, richly active dreaming in the final hours before natural waking, becomes blunted, arriving later, lasting less long, generating less vivid material to carry back. A graph of REM sleep across the full human lifespan looks like a river running gradually shallower. In infancy, it is wide and full, filling nearly half the bed of sleep. In childhood, it narrows. In middle age, it has settled into a steady, moderate channel. And in later years, it has thinned to something more modest, still present, still cycling, still producing whatever inner life it generates, but with less force and volume than before. The dreams of later life are not absent, but the biological conditions that favor their production and their retrieval are less generous than they were in youth. The hippocampal encoding that catches dream memory and converts it into something retrievable changes across the lifespan as well, with hippocampal volume itself declining in many older adults, and the sharp wave ripples that consolidate memory becoming less frequent and less precisely timed. There is something to sit with in that picture. The brain that dreams most richly, in the biological sense, that spends the greatest proportion of its sleeping hours in the neurochemical tide of REM that generates the longest and most continuous dream episodes, that has the most active hippocampal consolidation machinery working through the night, is a very young brain. An infant sleeps for half the day, and half of that sleep is REM, and in all of those hours the brain is doing something with enormous consequence, laying down the circuitry of experience, the architecture of emotion and memory and self. Whether that process generates anything like what adults call dreams, images, narratives, the felt sense of inhabiting another scene, is genuinely unknown. The brain is there, the activity is there, the rest is inference and silence. What can be said is that somewhere between the saturated REM of infancy and the compressed, fragile REM of old age, every human nervous system passes through the years of richest and most retrievable dreaming, and that those years are shaped not only by age, but by the particular biology of the body in question. Hormones matter here. The relationship between sex hormone profiles and dream recall is one of the more consistently reported findings in the literature on individual differences, not because the mechanism is perfectly understood, but because the pattern is too consistent to set aside. Across multiple large-scale surveys and laboratory studies, women report remembering their dreams more frequently than men do. They describe their dreams in greater detail. They rate the emotional intensity of their dreams higher. They report interpersonally complex dream content, dreams populated with more characters, more relational texture, more emotional negotiation between people, more often than male participants in the same studies. These are group-level tendencies, not universal absolutes. There are men who remember every dream in vivid detail, and women who almost never do. But the pattern is robust enough, replicating across independent samples in different countries and different decades to suggest that something biological is contributing alongside the personality and attentional factors that also predict recall. The proposed mechanism centers on estrogen's influence on the neurotransmitter systems most active during REM sleep. Estrogen acts on the neurons that release serotonin, shaping how that signal is produced and distributed. It also acts on cholinergic neurons, the acetylcholine releasing cells, whose flooding of the cortex during REM sleep creates the associative, emotionally plastic encoding environment described earlier. If estrogen subtly amplifies the activity of these systems during the follicular phase of the menstrual cycle, when estrogen levels are at their highest, then the REM sleep of those particular nights might be fractionally more vivid, more emotionally textured, and more richly encoded than the REM sleep of other nights. The difference may not be dramatic on any single night, but across weeks and months and years, a slight hormonal amplification of the dream encoding environment could accumulate into a measurable, reliable tendency toward richer and more accessible dream memory. Estrogen acting on a cholinergic neuron is not a visible thing. The neuron sits in the basal forebrain, dense with protein receptors along its membrane, and the estrogen molecule arrives, carried in the blood, crossing the membrane by diffusion, and binds. What follows is a cascade of molecular events that takes hours to fully unfold. Gene expression changes, protein synthesis shifts, the neuron's output during the next cycle of REM sleep is subtly altered. The change is too small to feel. The dream that results from it may not seem different from the outside, but somewhere in the difference between that night's encoding and another night's encoding, a memory trace is slightly more durable, slightly more emotionally charged, slightly more likely to survive the crossing back into wakefulness. The body keeps its own records of these changes in the texture and frequency of remembered dreams in ways that only become visible in the aggregate. The aggregate picture, built from structural neuroimaging, from genotyping, from hormone assays, from lifespan surveys of dream recall frequency, does not resolve into a simple story with simple causes. What it reveals instead is a set of overlapping biological influences, each one contributing a small independent increment of probability that a given brain, on a given night, will generate dreams rich enough to remember. The serotonin transporter gene shapes amygdala reactivity. The locus coeruleus determines how completely the brain's alerting signal is silenced during REM. Estrogen amplifies the cholinergic environment of dreaming sleep. The lifespan trajectory of REM abundance sets the overall volume of dream material being produced. And underlying all of these, the structural architecture of the default mode network and the temporoparietal junction determines how richly inhabited the dream narrative is and how strongly the brain's self-referential processing sustains the experience through the night. None of these factors works in isolation. A brain with high amygdala reactivity but poorly consolidated REM sleep may generate emotionally intense dream experiences that are too brief to be encoded. A brain with abundant late-night REM but low default mode network connectivity may produce long periods of dreaming that are flat and poorly organized, thin rather than thick, more weather than story. The factors interact, amplify each other, and sometimes cancel. What emerges from the interaction is not a category, high recaller or low recaller, but a continuous shifting, probabilistic tendency, different in every person and different in the same person at different points in life. The gray matter density of the medial prefrontal cortex is a useful place to end the biological picture because it holds both sides of the story at once. It is a cause. More neural tissue in this region means more capacity for the self-referential, narratively organizing processing that turns a stream of REM imagery into a coherent, emotionally inhabited dream that has a chance of being remembered. It is also a record. Neural tissue grows and is maintained in response to use, and a lifetime of attending to inner experience, of treating the interior landscape as something worth noticing, something worth returning to, may itself contribute to the gradual building of that substrate. The structure reflects the history. The history has shaped the structure, and both of them inseparably are what a person brings to the dark each night, when the body settles and the eyes close and the locus coeruleus begins its long descent towards silence. There is something quietly contemplative in understanding that the biological differences between a frequent dreamer and a rare one are not sharp. They are gradients distributed across many systems, operating at scales from the molecular to the anatomical, from the momentary chemistry of a single OIM cycle to the slow physical change of neural architecture across years. The brain that wakes with a dream every morning is not a fundamentally different kind of brain. It is a brain shifted slightly in several directions at once, a little more reactive in its amygdala, a little more structurally developed in its self-referential regions, a little more thoroughly silenced in its locus coeruleus during each REM episode, perhaps a little more richly sustained in its late-night REM cycles by the particular hormonal climate of its body. Individually, none of these differences would be enough. Together, they add up to a night that leaves more behind. The locus coeruleus, going quiet in the brainstem's deep architecture, is still the right place to rest for a moment. Not because it is the most important factor, no single factor is, but because its silence is so complete, so unlike anything in waking life, so precisely timed to the conditions under which the mind generates its most complex inner experience. That small cluster of cells, dense and blue, has been firing through the whole long day, regulating attention, signaling threat, maintaining the thread of waking consciousness with its steady chemical hum. And now, in the last hours before morning, it lets go. The norepinephrine falls away. The dreaming brain, freed from that signal, opens into something wider and less linear. What happens there, in the associative space opened by that silence, in the emotional coloring provided by the amygdala's heightened response, in the self-referential narrative sustained by the default mode network's long activity, in the structural capacity of prefrontal gray matter to hold and organize what the night generates, is partly universal and partly individual, partly fixed and partly shaped by years of attention, and entirely quietly the most complex inner experience the body routinely produces. By the time the locus coeruleus begins to stir again, slow and gradual, as the first light of morning begins its work on the circadian clock, the norepinephrine returning, the dreaming state beginning to dissolve, the body drifting toward wakefulness, what remains in memory is whatever survived the transition. In some brains, a great deal survives. In others, almost nothing. Between these two, across the full population of sleeping minds, there is a long, quiet spectrum of biological difference, shaped by genes, by hormones, by the accumulated structure of decades of living and attending, that determines, night after night, how much of the inner life persists into the morning, and how much dissolves with the silence that made it possible. The alarm sounds, and the dream is gone. Not slowly, not in pieces, all at once, the way a reflection disappears when a stone breaks the surface of still water. One moment there was a place, a light, a sense of something just understood, and then there was a ceiling, and the sound of morning, and nothing left of the night but a faint warmth, that had no name and no image attached to it anymore. This is the interference effect. Incoming sensory information, the volume and urgency of an alarm, the sudden orientation toward physical space, the muscular act of reaching out to silence a sound, floods the prefrontal cortex with new signals at precisely the moment when a dream memory is at its most fragile. The neural trace is not erased. It was never fully written. What the waking brain receives in those first alert seconds is more input than it can hold alongside something so thin and so recently assembled, and the dream simply falls away beneath the weight of the world arriving. There is nothing wrong with the brain that experiences this. It is doing exactly what it is built to do. The system that orients attention outward, that pulls the self back into space and time, and the reliable coordinates of a known room, is doing its job with great efficiency. The cost of that efficiency is the dream. What the brain does in the minutes before that alarm is a different matter entirely. Deep in the last hour of a full night of sleep, in the long, dense REM period that accumulates its weight in the final approach to morning, the dreaming brain is doing something that does not look like rest from the outside and does not feel like rest from the inside. Scenes are running. Memory traces are being retrieved and recombined. The emotional systems are active. The self-referential networks are lit. And somewhere in the hippocampus, coordinated bursts of electrical activity are attempting, with varying success, to convert what is happening in the dream into something durable enough to survive the return to waking. Whether they succeed depends on many things. Some of those things are written into the biology of a particular brain, its architecture and its chemistry, and the way its genes have shaped its sensitivity to its own inner life. Some of those things are shaped by age and by the slow changes time brings to the sleeping brain. Some of those things are lifted or lowered by habits so ordinary they do not feel like they could matter to something as elusive as a dream. What time a person sleeps, what they consume, how they have been feeling for the past several months, and whether they have trained themselves, however gently, to pause at the edge of waking and pay attention. It is this last category that is worth dwelling in now. A notebook sits on a bedside table in the early morning light. It is nothing elaborate. A plain cover, a pen tucked into the spine. It has been sitting there for 3 weeks, and in that time the person who placed it there has written in it every morning, before getting up, before speaking, before looking at a phone, not reconstructing a narrative, not reporting a coherent story, catching what is left. A color, a feeling of having been somewhere high, a name that does not belong to anyone known. The sense of urgency around something that made no sense but felt entirely real. A few sentences at most, sometimes only a word or two, written in the slightly effortful hand of someone who is not yet fully awake. This practice, recording whatever remains of a dream as soon as possible after waking, has a measurable effect on how much of a dream is remembered, and how often dreams are remembered at all. Research by Michael Schredel and colleagues found that consistent dream journaling increased recall frequency and the rated level of detail in recalled dreams after as little as 2 weeks of regular practice, with the effects continuing even beyond the period of active journaling. The mechanism is not a single thing, but likely a combination of 2 processes working together. The first is prospective memory priming. When the sleeping brain has been given a consistent behavioral signal, the act of attending to dream content upon waking, recording it, giving it time and deliberate focus, it may begin to preserve fragile dream traces more readily, as though the system has been informed that this material will be wanted. Attention directed toward dream recall in the first minutes of each morning appears to prime the brain to make that recall easier the following night. The act of reaching for what remains conditions the brain, over time, to hold it a little longer. The second process is retroactive trace deepening. Writing a dream down, even incompletely, even in fragments, forces the brain to reconstruct what it has, and in doing so strengthens the neural pattern that represents it. The act of retrieval, imperfect, partial, halting, is itself a form of memory consolidation. The words on the page become a second encoding, an external representation of an internal event, and the memory of having written them can anchor the dream to waking experience in a way that passive recollection alone cannot. The notebook lies open, the pen has stopped moving. What is written there is spare, 3 lines, a color, the word for a feeling, and it represents a world that existed only in one sleeping mind, a complete environment with its own gravity and logic and light, compressed now into the smallest possible record of itself. Without the notebook, it would be gone entirely. With it, something remains. The act of reaching for a dream is itself a discipline, and like most disciplines, it becomes easier with practice. But there is a more fundamental act that the notebook depends on, one that happens even before the pen touches the page, in the first seconds after the eyes open, lying still. The critical window for dream recall is not the hour after waking, or even the 10 minutes after waking. It is the 2 minutes, the first 2 minutes, when the dreaming brain is still close enough to its own recent activity that the traces have not yet been overwritten by the organizing imperatives of the day. Movement accelerates the transition. Sound accelerates it. The cognitive demand of orienting to a space, calculating the time, remembering the day's obligations, all of these pull the prefrontal cortex into executive mode and the dream out of reach in the same motion. Lying still, eyes closed, attention directed back toward whatever is fading. This is not passivity. It is a specific and deliberate act of counter-pressure against the interference effect, the only window in which it is possible. Some people have already left by the time that window opens. The alarm has done its work, and they are already up, already moving, already in the logic of the waking day. For those people, the dream is not retrievable. It was never given the space to be. Others find, over time, that they can hold the window open a little longer. Not through effort, not through concentration in the strained and narrowing sense, but through a kind of patient inward stillness, a willingness to remain at the edge of sleep without crossing back into it, turning attention toward the last interior image with the same quality of waiting that a person uses to hear something very quiet in a room that is almost but not entirely silent. This quality of attention, calm, patient, non-reactive, directed inward, has been associated in research literature with something much older and more practiced than a bedside notebook: meditation. In the early morning, in a room that is quiet but not silent, a person sits in a posture that is comfortable enough to hold without strain. Their eyes are closed or lowered. They are not trying to make anything happen. They are practicing non-judgmental awareness of internal experience, noticing what arises, watching it change, staying present with whatever is occurring in the body and the mind without reaching for it or pushing it away. Thoughts come. They are noticed and allowed to pass. Sensations arise. They are observed without commentary. This is not a passive activity, despite its stillness. What it is training, session after session, morning after morning, over months and years, is the brain's metacognitive monitoring capacity, the ability to observe its own processes from the inside, to notice what is happening in consciousness without being immediately and entirely absorbed by it. And this capacity, the research suggests, is precisely what the brain calls on when it attempts to catch a dream before it dissolves. Regular mindfulness-based meditation practice has been associated in multiple studies with increased dream recall frequency, greater rated vividness in recalled dream content, and higher rates of lucid dreaming, the state in which a dreamer becomes aware during the dream that they are dreaming. The mechanisms proposed for these associations involve changes in prefrontal regions implicated in self-monitoring and in the structural development of the very brain areas that hold fragile memory traces across the threshold of waking. Long-term meditators show measurable structural differences in these prefrontal regions, with greater gray matter in areas associated with sustained attentional control and the regulation of internally generated experience. There is something here that is not precisely about meditation and not precisely about dreams, and is yet about both. The skill of noticing, the practiced ability to orient attention gently towards something faint and interior without collapsing the distance between observer and observed, to look at the dream without grabbing for it, to remain at the edge of it long enough for something to come clear. This same quality of attention, turned inward in the first moments of waking, is what the brain uses to hold open the fading image. And because it is a skill that can be developed, not through effort, but through patient practice, it suggests that the gap between a person who never remembers their dreams and a person who remembers them every morning is not necessarily fixed, not necessarily written into biology alone, but is at least partly the gap between two habits of attention, two ways of meeting the transition from sleep. Attention, though, is not the only variable. The brain that tries to remember a dream is not operating in a constant neurochemical environment. It is operating in whatever environment the preceding day and night have left behind, shaped by stress, by substances, by the debt or surplus of sleep accumulated over days or weeks. These conditions do not merely affect the quality of sleep. They change the nature of the dream itself, and in doing so, they change what there is to remember. Stress is the most common and the most complex of these influences. A person lies awake at 2 in the morning, not from insomnia, but from the residue of a day that has not finished processing. The cortisol levels that drive the stress response and that normally fall through the night toward their pre-dawn nadir have not fallen as cleanly as they should. The amygdala, the brain's emotional signal processor deeply embedded in the medial temporal lobe, has been running warm all day, responding to pressures real and anticipated, and it does not simply switch off when the body lies down. In REM sleep, the amygdala is already active, already engaged with the emotional content of the dreams it is helping to generate. Elevated stress in the preceding hours amplifies that engagement, producing dreams that are more emotionally saturated, more vivid, more insistent, and for that reason, more likely to be remembered. This is the moderate stress effect. Under conditions of ordinary manageable pressure, the emotional loading of dream content rises, and with it the salience of the dream as a candidate for memory consolidation. The brain gives priority to emotionally significant information. A dream that carries real emotional weight is harder to lose than a neutral one. But this relationship between stress and dream recall is not linear, and it does not stay useful as stress increases. Under conditions of severe chronic or traumatic stress, the system tips. In post-traumatic stress, dreams are not merely more vivid, they become recurring, intrusive, and consolidated with a force that most other dreams do not approach. The same mechanisms that make emotional salience a driver of dream memory when pushed to an extreme, produce the nightmares of PTSD, fragments of experience encoded in the amygdala with such intensity that they replay with the compulsive regularity of deeply grooved neural pathways. At the furthest end of this continuum, where stress has persistently disrupted REM sleep architecture itself, fragmenting sleep, compressing or disorganizing REM episodes, altering the timing of the nocturnal cortisol cycle, recall can paradoxically diminish, not because there are fewer dreams, but because the neural conditions for consolidation have been sufficiently eroded that even vivid dreams leave less behind. Moderate stress and dream recall move together, gently. At the extremes, they come apart. The person lying in that early morning stress has a more charged interior night than a person sleeping in genuine calm. Whether they carry it back depends on how much of the structural machinery of dream consolidation remained intact through the stress and on what they do in the first minutes after waking. Not every source of interference arrives through the mind. A glass of wine on the bedside table, half empty from the hours before sleep, a social evening, a comfortable couch, the habitual glass that has been part of the wind-down ritual for years. By morning, the alcohol has been metabolized, and its acute sedative effects have passed, and the night might feel from the outside like a normal one. But what the night actually contained was not quite normal, not in its architecture, and not in its dreaming. Alcohol acts on the brain through the GABA neurotransmitter system, increasing inhibitory signaling in ways that initially produce sedation and promote the descent into sleep. In the first half of the night, this produces something that looks like deep, restful sleep, but REM is suppressed. The cycling that would normally have produced the first REM episode within 90 minutes or so of sleep onset is delayed or blocked. The first two cycles of the night pass with little or no dreaming. Then, in the second half of the night, as the alcohol metabolizes and its suppressive effect withdraws, REM rebounds, a surge of the compensatory pressure that has been building since the first cycle, and the second half of the night is heavy with the kind of compressed, fragmented, restless REM sleep that produces vivid and sometimes disturbing dream content, but in a state of sleep that is lighter, more disrupted, and less conducive to smooth memory consolidation. The morning after, the person remembers less, not more. The first half of the night left no dreams. The second half left sleep too disrupted for easy recall. What might have been 3 or 4 distinct dream episodes across a full architecturally clean night has been compressed and broken, and what remains in waking memory is often nothing, or at most a fragment of the final hour. This suppression is measurable, reliable, and dose-dependent. Even moderate amounts of alcohol consumed within 3 to 4 hours of sleep affect the distribution of REM across the night in ways that reduce dream recall for that night, and in regular drinkers, reduce it chronically. The nightly ritual that feels like preparation for rest is, in terms of dream experience, a nightly subtraction from it. Cannabis produces a parallel effect through different chemistry. The THC in cannabis acts on cannabinoid receptors in the brainstem circuits that regulate REM generation, and regular use at doses sufficient to produce a subjective effect substantially reduces the amount of REM sleep generated across the night. Long-term regular cannabis users frequently report that they do not dream at all, or at least that they do not remember dreaming, and this is not a misperception. Their REM sleep has genuinely been reduced, and with it, the dreaming it would have sustained. What happens when they stop using it is one of the more vivid demonstrations in the sleep science literature of just how powerfully the brain drives REM sleep when given the opportunity. On the first nights of abstinence, sometimes even on the first night, the compensatory pressure for REM sleep that has been suppressed, sometimes for months, sometimes for years, rushes in. The phenomenon is called REM rebound. The sleeping brain, freed from the inhibitory action of THC on its brainstem circuits, produces REM episodes that are longer, denser, earlier in onset, and more continuous than normal. The dreams that fill these extended REM periods are frequently reported as overwhelming in their vividness, emotional intensity, and narrative complexity, full of color and movement, and the faces of people not thought of in years, full of the emotional residue of experiences the brain has been storing without the nightly processing that REM sleep normally provides. Former cannabis users in the first weeks of abstinence sometimes described their dreams as more real than waking, not as a metaphor, but as a report of how the experience feels from the inside. This REM rebound is not limited to substance withdrawal. It occurs after any form of substantial sleep deprivation, and in a more familiar and more commonly experienced form, it happens after a run of short nights, the accumulated sleep debt of a busy week paid back, in part, on the first long night of recovery. The mechanics of this are built into the biology of the sleeping brain. Across a night of insufficient sleep, a compound called adenosine accumulates. It is one of the byproducts of the metabolic activity of neurons, the cellular waste of a brain that has been working, and it acts as a signal to the body that rest is needed. As adenosine levels rise through the night, they apply increasing pressure toward the deeper and more restorative stages of sleep. Under normal conditions, this pressure is discharged across the night, and the brain wakes refreshed and in balance. After insufficient sleep, the discharge is incomplete. The adenosine pressure that was not spent carries forward, building toward the next sleep period like a tide held back from shore. When that pressure is finally released, on a recovery night, a weekend morning with no alarm, a night given over entirely to sleep, the sleeping brain does not simply continue where it left off. It compensates. It drives sleep harder and deeper, and it drives REM sleep specifically with a force proportional to how much has been missed. The REM episodes that fill a recovery night are longer than those of a normal night, denser in content, richer in the associative and emotionally charged material that characterizes the deepest and most active dreaming, and they are more likely to be close to waking when they occur, longer, later, and more proximate to the moment of natural awakening. The result is familiar to almost anyone who has slept late after a stretch of short nights. A dream so vivid and complete that it stays with the sleeper through the entire following day, appearing and reappearing at the edges of ordinary thinking, not fading but returning, the way a piece of music returns, unbidden, to a mind that cannot quite release it. The detail of a face, the specific quality of light in an imagined room, a conversation that did not happen but felt in its emotional texture, entirely real. For researchers, this REM rebound is something more than an interesting experience. It is a window, because it reliably and predictably converts people who rarely remember their dreams into people who remember them with great clarity. It offers a natural experimental condition in which the upper bound of dream salience can be observed in ordinary people without laboratory intervention. What it shows is that the machinery for vivid dreaming is present in almost everyone. It does not belong exclusively to those who describe themselves as frequent dream recallers. It is not a fixed trait or a stable biological category. It is, at least in part, a state, a condition of the sleeping brain that can be reached by many different paths, from the gradual accumulation of sleep debt to the cessation of a substance that had been quietly suppressing it, to the chance alignment of a full night of undisturbed sleep with a late morning awakening from a long final REM period. The person who says they never dream has almost certainly been dreaming every night. They have simply been waking in conditions too abrupt, too sleep-deprived, too disrupted, in which the memory of the dream did not survive the transition. The experience was there. The neural event occurred. What was missing was the window, the stillness, the chemical and temporal conditions in which something so brief and so quietly assembled could be held long enough to be known. There is something quietly significant in this. The gap between a person who remembers every dream and a person who remembers none is not necessarily the gap between two fundamentally different kinds of brain. It may be in part the gap between two sets of conditions, biological, chemical, behavioral, attentional, some of which are fixed and some of which are not. The biology is real. The structural differences in the temporoparietal junction and the medial prefrontal cortex are real. The genetic predispositions toward emotional reactivity and interoceptive sensitivity are real. These cannot be changed by deciding to keep a notebook, but they are not the whole story. The alignment of conditions under which any brain produces its most vivid and most memorable dreams is not a rare accident reserved for a particular type of person. It is something that can be approached through the slow adjustment of sleep timing, giving the final REM periods the space to run to their natural length rather than cutting them short with an alarm, through the removal of substances that have been quietly reshaping the night, through the cultivation of a waking practice that turns attention gently inward before the day arrives, that trains the brain to hold the threshold open a moment longer, through the simplest of all possible acts, a notebook, a pen, and 2 minutes of stillness before the world begins. These are not large changes. They do not require extraordinary effort or unusual talent. They require only the kind of patient, repeated attention that the brain is already giving to everything it finds worth keeping. And what is kept, in the end, is worth something. Not because dreams are messages to be decoded or problems to be solved, though some traditions have treated them that way for as long as people have been recording the things that happen when they sleep. They are worth something for a simpler reason and a deeper one. A dream is a full experience. It has the texture of a real world, real light, real voices, real emotional gravity, real consequence within the space it inhabits. The brain that generates it is working, processing, consolidating, integrating the emotional material of the days that have led to this particular night, finding patterns in experience that the waking mind, occupied with its sequential and practical thinking, did not have the time or the freedom to find. That work continues whether or not the dreamer is aware of it. The brain does not require that its nighttime activity be remembered in order to continue doing it. The emotional processing of REM sleep, the reweaving of memory traces across the night's slow architecture, the gradual reorganization of experience into something that can be carried forward, all of this happens in the dark, with or without a record. But there is something that changes when the record is kept. Something that happens when a person develops the habit of reaching back for what remains of the night, writing it down in the first uncertain light of morning, paying attention in the particular way that dreaming asks to be attended to, with patience, with the willingness to hold an image without forcing it into sense, with the tolerance for something that is whole in its own way, but does not translate cleanly into the grammar of the waking day. That something is, in a quiet way, a form of relationship with the self. The brain at night is not the same as the brain in the afternoon. It has a different chemistry, a different hierarchy of concerns, a different relation to emotion and image and time. The dreaming mind is not constrained by the usual requirements of logical sequence or social performance. It assembles the material of a life according to its own principles, returning to what carries weight, lingering on what has not been resolved, combining things in ways that are sometimes illuminating and sometimes simply strange, and sometimes both at once. To remember this, even imperfectly, even in fragments, to bring something of that interior life back across the waking threshold, is to know something about the mind that it would not otherwise be possible to know. The notebook lying open in the early morning light holds a few sentences from one night. The handwriting is slightly unsteady, the grammar not quite right, the images half described, but what is there is real. It happened. The mind that wrote it was present in that room, in that imagined space, experiencing something with the full weight of experience, and then it carried that something back, which is a thing that takes effort and practice and a particular quality of attention, and is not nothing. A meditator sits in the early morning stillness, practicing the patient noticing of what arises and what passes. The skill being built there, the capacity to observe the mind's own movement from a slight distance without being pulled entirely into it, without recoiling from it, is not so different from the skill of lying still after waking, eyes closed, turning attention gently back toward the last fragments of a dissolving image. The patience, the non-grasping quality of the attention, the willingness to wait, both involve the same basic orientation, the mind facing inward, the mind watching itself, the mind discovering in stillness that there is more happening inside than is visible from the surface. Sleep brings this every night to every brain. The question of whether any of it is remembered depends on a long chain of conditions, some biological, some architectural, some chemical, some behavioral, and at the end of that chain, on a single, small, repeatable act. The act of choosing, in the first soft moments of waking, not to move toward the day immediately, but to pause, to remain at the edge, to hold open the door through which the night's experience might still faintly pass. The alarm sounds. In this version, the sleeper reaches out and silences it slowly, then lies still again, eyes closed. There is something there, not a full scene yet, more a feeling, the sense of having just come from somewhere, a quality of light, a direction. If attention is turned toward it now, gently, without demanding that it become coherent all at once, it may take a little more shape, a place resolves, then a figure at the edge of it, then the sense of something that mattered, the emotional truth of it arriving before the details do, the way music's feeling arrives before the melody is placed. There is a pen on the table. There is a notebook open to a blank page. The writing is slow and a little imprecise, because the hand is not yet fully awake, and because precision is not what is needed. What is needed is catching, a few words for the light, a word for the feeling, the name of the place, even if the name is wrong, even if it is only the closest word for something that had no real equivalent in waking life. The entry fills a quarter of the page, then the pen is set down. Outside, the morning has been continuing without any of this. The light has been doing what it does. The world has been filling with its familiar sounds. The day has been assembling its requirements. All of that was waiting, patient, and it will wait a little longer.